Subject Geology. Name of the paper Economic Geology and Mineral Resources of India. Name of the module Deposits related to clastic sedimentation, placer deposits. Objectives: to understand processes and mechanisms of development of placer deposits, field occurrences of residual, alluvial, beach, offshore and Aeolian placers, and ore potentialities of placers with examples. Introduction. Placer deposits may be defined as a special type of clastic sediment, unconsolidated or semi-consolidated, sedimentary or its metamorphic equivalent, with economic grade concentration of one or more valuable, dense, resistant minerals. This is an archetypal sedimentary ore in the strictest sense of the term, and the only type where the chemistry of the fluid that transports and deposits the material does not have any significant role. Instead, the physics of fluid flow as conditioned by the prevailing tectonic, geomorphic and climatic conditions and its interplay with particle density, size and shape determine the emplacement sites and tenor of such deposits. Mukherjee, 1999. Today, considerable portions of global supply of native gold, platinum, diamond, rutile ilmenite, zircon, monazite, uraninite, columbite tantalite, cassiterite, varieties of gemstones and RE minerals are recovered from placers, besides some reworked detrital chromite, bauxite, kyanite, manganese oxide and iron oxide, boulder ores and conglomeratic iron ores. According to an estimate made in 1989, about 48% of gold, 55% of tin, 62% of zinc ore, 51% of bauxite and 18% of uranium ore of the world occur in detrital sedimentary placer deposits. Commonly used classification of placers are based on A. Medium of transport, namely water, wind or ice. B. The environment of deposition. C. The environment of preservation. D. The distance of transport from the source provenance. E. The composition of the ore. Optimal condition for development and preservation. Minerals concentrated in placer deposits possess three common attributes. They all have high specific gravity, high malleability or toughness or hardness, and are all chemical weathering resistant. Their source could be A. Lean or rich lodes including pegmatites, disseminated ores and stockworks. B. The underlying podzolized bedrock itself in case of residual placers. Or C. The accessory minerals present in the rocks of the distributive provenance. For some multi-component, namely zircon, monazite, ilmenite, rutile, garnet, beach placers, the source regimes are usually the vast, deeply exhumed metamorphic igneous complexes. The distributive provenance ideally should have pronounced topographic relief and or a history of rejuvenation through uplift and be located within a favorable climatic zone where deep chemical weathering is prevalent, ensuring a continuous supply of disaggregated placer minerals over a protracted period. The depositional environment for placers ideally must offer opportunity for reworking. Hence, the requirements are A. Low subsidence rate of the basin, B. High depositional energy, C. Protracted crustal stability, and D. Moderate sedimentation rate. Processes and mechanisms of development of placer deposits. An understanding of the processes of transport and deposition of clastic sediments is a prerequisite for deciphering the mechanism of placer formation. A loose, incoherent but undispersed mass of wet or dry clastic sediment behaves as a solid of low strength that resist any deformation or erosion until the applied shear stress exceeds a critical value, when either the mass as a whole begins to be sheared or the grains from its upper surface begin to erode away. Movement of grains is impeded by gravity and by friction among mutually touching grains and becomes possible only when some mechanism can effectively counter these forces, enabling the grains to be lifted and or slide past one another. Sediment in motion class or grains is called load. The load material may be derived from river beds, the bed material load, or from the eroding banks and tributary drainage slopes, called the wash load. Sediment load supported by the turbulent fluid flow or upwelling and moving well above the channel bottom are called suspension load, and those moving close to the bottom are termed bed load. Bed load, whose weight is totally supported by contact with the base, is termed contact load, which moves by the traction of water flowing over it, while the bed load supported by intermittent contact with the base moves mainly by saltation or repeated bouncing. At low speed, air and water flow smoothly, called laminar flow, while at high speed, the flow becomes turbulent with eddies and vortices. Turbulence is the principal cause of suspension of sediments as long as the vertical component of the turbulent velocity fluctuations exceeds the settling velocity. Increasing velocity of a flowing medium over a sand bed affects gradual transition of the mode of particle transport from intermittent rolling to saltation to suspension. Besides turbulence, other factors that affect particle suspension are A. The buoyancy, which is a function of fluid density enhanced by the suspended particle themselves, and B. The upward flow of interstitial fluid, both of which dampen the settling velocity of grains. Liquefaction of loosely packed unconsolidated sediments takes place when the whole mass loses its strength and can move even with 1 to 2 degree slope as the weight of the grain is transferred to the pore fluid. Fluidation is a special case of liquefaction triggered by pumping fluid through sediment mass. Sediment movement by waves, which in deep water produces rotational motion of water, has different kinetics. The movement of water particles at the surface traces circles with diameter equal to wave heights. The diameter and therefore the velocity of orbital motion decreases exponentially with depth, so that the sediments at the bottom are particularly undisturbed by the waves. In relatively shallow water, waves interact with the bed, producing an oscillatory motion of water at the bed. In very shallow water, waves become steep and eventually break down where the depth is 3/4 times the deep water wave height. Plunging waves at the breaking point pick up profuse sand-sized particles, while the oscillatory motion is converted to a transitional turbulent bore that moves up the beach and returns as backwash. The combined action of the onrush and backwash, aided by strong beach parallel current within the surf zone, produces strong movement of sand along the beach within the surf zone, that is the longshore drift. These interlinked mechanisms are capable of producing rich concentration of placers. In all the cases discussed so far, sediment motion is incidental to and a consequence of gravity-induced fluid motion. In contrast, situations arise as in a turbulent current where gravity-induced movement of the sediment causes fluid movement. Gravitational pull on the suspended particles causes the entire suspension to move downslope into deeper waters, the movement of suspended particles creating turbulence, and the turbulence in turn keeps the particles in suspension. Natural turbidity current can carry hundreds of cubic kilometers of sediments over distances of several kilometers. Mechanisms of development of placer deposits can be discussed by considering the processes in two end-member depositional environments of fluvial and shoreline regimes separately. For while the fluid flow is always unidirectional and its gradient, vector and load vary from place to place and at the same place over time, the shoreline regime witnesses effects of rhythmic alteration or interplay of the onrushing, decelerating, turbulent breaker waves and the accelerating laminar backwash in opposite directions, affecting mainly the basal carpet load. Shape and size analysis of heavy minerals in clastic sediments unequivocally demonstrate that the heavy mineral grains are invariably much smaller than the accompanying quartz and feldspar grains of the matrix. This is primarily due to sorting by flowing medium. Shape and size analysis of clastic sediments indicate that the settling velocity of the spherical particle is proportional to its fluid immersed specific gravity and the square of its radius, which is Stokes' law. Fall velocity is an important factor in segregation of heavy minerals. Grains of different minerals having the same settling velocity would float, remain suspended, or sink together. Sorting of mineral grains is a function of density, size, and shape of grains in suspension or under traction, and also of the nature of the fluid flow. The contrast between specific gravities of two minerals is accentuated when both are immersed in water. The denser mineral grains having smaller surface areas offer less friction and hence sink faster. A flattened grain with higher surface area than a spherical grain of same mass and or density tends to remain suspended when the latter sinks down. For the bed or carpet load materials, the grain size and shape assume even more significant roles and the grain density becomes a secondary factor. Larger and inequidimensional grains sticking out in the flowing medium are much more susceptible to dislodgement by lever action than smaller equant grains. The concept of hydraulic equivalence in the context of transportation and deposition of heavy minerals relates to size of heavy mineral grains to the size of quartz grain with same settling velocity. For instance, an equant magnetite grain with specific gravity 5.18 of 0.2 millimeter diameter is the hydraulic equivalent of a rounded quartz with specific gravity 2.65 of 0.5 mm diameter. Grigg and Rathburn 1969, Slingerland 1984, Force 1991 and others articulated the three types of hydraulic equivalence, namely settling velocity, entrainment equivalence and transport equivalence need to be considered. Placer enrichment often takes place due to sequential operation of these different equivalence laws. Settling velocity relationship is valid for particles in suspension. Placer enrichment in a single bed due solely to settling equivalence among minerals can take place when the supply of lighter quartz and feldspar grains of appropriate size equivalence is depleted, while the grain size of the supplied heavy minerals lies within the required size range dictated by the depositing flow. Entrainment equivalence relates to the shape or size equivalence of finer, denser mineral grains required to be uplifted along with the larger light mineral grains of a particular size range from the carpet load. Coarser, low-density mineral grains are thus selectively and preferentially salted from the bed load, thus enhancing the concentration of heavy minerals at the site. Transport equivalence is governed by kinetic factors and involves both settling and entrainment equivalence factors. A dynamic lag enrichment of heavy minerals occurs when grains of those minerals finer than the settling equivalent and size range for the lighter minerals. If the transporting fluid medium is fed with heavy and light mineral grains of same average size, the heavy ones tend to lag behind due to their higher settling velocity. Sequential operation of settling and entrainment loss of equivalence can produce a high degree of enrichment of placers. Once a bed is marginally enriched in finer dense minerals in a matrix of coarse lighter mineral grains, subsequent operation of the entrainment equivalence principle leads to selective removal of the larger lighter materials. Interstice entrapment involves the movement of smaller heavy mineral grains into the interstices of coarser sediment, as a result of which gravels will be better traps than sand. This results in fine grains commonly lagging behind coarse grains when both are being transported over coarse bed and dynamic lag enrichment of heavy minerals are built up. Slingerland, 1984. The beach placers, usually far more enriched than fluvial placers, furnish the most instructive example of sequential and/or overlapping operation of equivalence loss. An onrushing turbulent breaker front, charged with suspended particles with diminishing velocity, lays down successive strips of progressive finer sediments landwards. In each stripe parallel to the wavefront and coastline, grain sizes of the light and heavy minerals are hydraulically equipoised. The backwash lamellar flow of a previous wave starts with no suspension load and accelerates progressively seawards, plucking out preferentially the larger, lighter mineral grains from the carpet according to the entrainment equivalence principle with increasing efficiency as it gradually accelerates. Thus, high up on the swash face, most of the larger and lighter mineral grains are plucked off and removed, and most of the heavier and finer grains are retained in response to entrainment equivalence requirement, thereby producing heavy mineral enriched stripe. Further down, as the velocity of backwash increases, the entire batch of grains may be lifted up in the flow. The denser grains would, however, quickly sink to the bottom, lag behind during transport, and would lie on an enriched layer few millimeters below the surface after the passage of the return wave. The resulting package then would be an inversely graded bed with coarser light mineral fraction atop finer heavy mineral grains. Classification of placer deposits. Placers can be classified in various ways, but the simple, traditional and genetic classification provided in the textbook on economic mineral deposits by Jensen and Bateman considered the placers into 6 types. A. Residual placers, accumulation developed in situ as a result of weathering. Alluvial placers, concentration in a moving medium. C. Stream or alluvial placers. D. Beach placers. E. Offshore placers. C, D and E are concentrations in moving water, also designated as fluvial, strandline and marine placers respectively by MacDonald, 1983. And F. Aeolian placers, concentrated in moving air, designated as desert or coastal alien by MacDonald, 1983. Residual placers. These accumulate immediately above a bed source, example gold or cassiterite veins, by the decay and removal of light rock materials, and they may grade downwards into weathered veins. In residual placers, chemically resistant light minerals like beryl may also occur. Residual placers only form where the ground surface is fairly flat. When a slope is present, creep will occur and alluvial placers will be developed, as shown in figure 1. Residual placers formed over carbonatites are important as producers of apatite, like at Jacupiranga, Brazil, Sokli in Finland, and Sukulu in Uganda. They are also sources of zircon, badellite, magnetite, and other minerals. These residual placers have often formed on carbonatites, which are themselves subeconomic. Chemically resistant anatase deposits developed in the weathered overburden of 3 alkali stocks in Parana Basin, Brazil, constitute some of the world's largest titania deposits, about 300 metric tons grading 20% or more of anatase. These deposits, although of residual origin, are not considered as residual placers owing to the fact that these anatase accumulations are admixed or partly cemented with residually altered or weathered silicate minerals of the parent alkalic rocks. Alluvial placers. These are formed on hill slopes from minerals released from a nearby source rock. The heavy minerals collect above or just downslope of the source, and the lighter non-resistant minerals are dissolved or swept downhill by rainwash or are blown away by the wind. This produces a partial concentration by reduction in volume, a process which continues with further downslope creep. Obviously, to yield a workable deposit, this incomplete process of concentration requires a rich source. In some areas with alluvial placers, the economic material has accumulated in pockets in the bedrock surface, like cassiterite in potholes and sinkholes in marbles in Malaysia. Cassiterite is obtained in abundance from alluvial deposits in Myanmar, Thailand, Vietnam, Zaire, Nigeria, Australia, apart from Malaysia. Alluvial kyanite boulders of high purity are gathered or washed out from the regolith in India. Stream or alluvial placers. Stream placers were once the most important type of placer deposits and have yielded large quantity of placer gold, cassiterite, platinum, and precious stones. It is well known that heavy mineral fraction in sediment is much fine-grained than the lighter mineral fraction. The sorting and composition of sediment is controlled by both the density and size of the particles, known as their hydraulic ratio. Thus, a large quartz grain requires the same current velocity to move it as a small heavy mineral. Clearly, if we have a very rapid flow, all grains of sand grade will be in motion, but with a slackening of velocity. The first materials to be deposited will be large heavy minerals, followed by smaller heavy minerals plus large grains of lighter minerals. If the velocity of the transporting current does not drop any further, then a heavy mineral concentration will be built up. For this reason, such concentrations are developed when we have irregular flow, and this may occur in a number of situations. The first example is that of emergence from a canyon. In the canyon itself, the net deposition is zero. As the stream widens and the gradient decreases at the canyon exit, any heavy mineral will tend to be deposited and lighter minerals will be winnowed away. Relatively coarse minerals can be expected to be concentrated in riffles in a stream bed. Riffles are transverse linear features, as shown in figure 2 and 3, that range in size from hairline joints through fracture and faults to transverse dikes or contact between resistant and non-resistant strata. Heavy minerals will also be retained preferentially in plunge pools, in eddy pools, in rapids and potholes. One of the richest placer gold occurrences in mining history was a few square kilometers of potholes and karstic crevices and cavities in a limestone portion of the streambed of Calaveras River near Columbia, California. These pockets yielded 120,000 kg of gold in 15 years prior to 1986, with nuggets of up to 30 kg in the coarse gravel pothole fillings. Coarse heavies will also accumulate with much coarser pebbles. Cobbles of durable rock types as lag materials in the cut banks and channels of streams. Fine-grained heavies associated with clays and silts may accumulate in the slack water areas on slip slopes or in velocity shadows below stream confluences. Rapidly flowing meandering streams also provide sites for deposition of heavy minerals. In the meandering rivers, faster water is on the outside curve of the meanders and slack water in the opposite. The junction of the two, where the point bars form, is a favorable site for deposition of heavy minerals. With lateral migration of the meander, a pay streak is built up which becomes covered with alluvium and eventually lies at some distance from the present stream channel. Placer deposits do not form in the meanders of old rivers because the current flow is too sluggish to transport heavy minerals. In the upper reaches, current flow may be too rapid and there may also be a lack of source material. The middle reaches are most likely to contain placer deposits where we have graded streams in which a balance has been achieved between erosion, transportation and deposition. Gradients measured on a number of stream placer, gold and cassiterite deposits average out at a little under 1 to 175, that is moderate gradient of about 6 meters per kilometer. The most important minerals of beach placers are cassiterite, diamond, gold, ilmenite, magnetite, monazite, rutile, xenotime and zircon. Examples include the gold deposits of Nome, Alaska, diamondiferous gravels of Namibia, Angola, ilmenite, monazite, rutile sands of Travancore and Quilon, India, ilmenite, zircon, leucoxene bearing sands of Richards Bay, South Africa, rutile, zircon, ilmenite sands of Eastern and Western Australia, magnetite sand of North Island, New Zealand, and titania leucoxene deposits in elevated sandbars of Eastern Florida, United States of America. Leucoxene of the beach placers is a weathered product of ilmenite with about 52% TiO2 and is enriched with TiO2 as a consequence of leaching of iron. TiO2 content in leucoxene exceeds 70%. It is the preferred feedstock for production of titania and titanium by much preferred, less pollution causing chloride process. For generation of beach placers, source or sources of the heavy minerals must be present. These may be coastal rocks or veins cropping out along the coast or in the near shore, seabed or rivers of older deposits being reworked by the sea. Recent and subrecent beach placers occur at different topographical levels owing to Pleistocene sea level changes, as shown in figure 5 and 6. The optimum zone for heavy mineral separation to occur is the tidal zone of an unsheltered beach, but concentration may also occur on wave-cut terraces. Some raised beaches formed during high Pleistocene sea levels contain placer ores such as at Nome, Alaska. Beach placers are formed along shorelines by the concentrating agency of waves and shore currents. Waves throw up materials onto the beach, the backwash carrying out the larger, lighter mineral grains, which are moved away from longshore drift, the larger and heavier grains thus being concentrated on the beaches. Heavy mineral accumulations can be seen on the present day beaches to have sharp bases and to form discrete laminae. They are especially well developed during storm wave action. Inverse gradient is present in these laminae. At the base, there is a fine-grained and or heavy mineral-rich layer which grades upwards into coarser and or heavy mineral-poor sands. These laminations develop during backwash phase of wave action. The breaking wave moves sand into suspension and carries it beachward, and as its velocity drops, its load is deposited. Subsequently, the water flow reverses and a surface layer of sand is disturbed, becoming a high particle density bed flow. During such a bed flow, the smaller and denser particles sink to the bottom of the flow, producing the reverse grading and also helping to concentrate the heavy minerals. The heavy mineral poor sand is thus closest to the surface, waiting to be removed by the next wave. A considerable tidal variation is also important in that it exposes a wider strip of beach to wave action, which may lead to the abandonment of heavy mineral accumulations at the high water mark, where they may be covered and preserved from erosion by seaward advancing Aeolian deposits. These occur on the continental shelf region, usually within a few kilometers of the coast. They have been formed principally by the submergence of alluvial and or beach placers. Well-studied examples are the offshore cassiterite placers of Indonesia. Offshore placers are becoming increasingly important as heavy mineral producers, and with the development of more efficient dredges that are capable of working along storm-affected coastlines, they may help in prolonging the life of such deposit types. For example, it is estimated that the life of TiO2 offshore sands of Hainan, China would increase from 28 to 56 years with the introduction of more efficient dredging. Such dredges also would enable exploitation of the newly found 10 to 15 meter deep monazite-rich sands of north and southwestern coasts of Sri Lanka. These occur at a distance of 8 km offshore. Aeolian placers. The most important of these have formed by reworking of beach placers by winds. Example, the large titanomagnetite sand deposits of North Island, New Zealand that are estimated to contain more than 1,000 metric tons of titanomagnetite. Coastal Aeolian dunes have great volume and homogeneity, and those with significant contents of heavy minerals can be economic even at low grades. Coastal dunes are of three main types: foredunes, transgressive dunes, and stationary dunes. Foredunes occur immediately adjacent to present or fossil beaches. Transgressive dunes have migrated inland from beach deposits and consist of long wall types still parallel to but now detached from the shoreline. Clifftop coastal dunes are parabolic accumulations on cliff or other steep shorelines. The Jennings-Ennebar deposit of Western Australia, about 350 km north of Perth, appears to have formed as clifftop dune. High-grade Aeolian deposits at Richards Bay on the Natal coast, South Africa, occur in a belt along the modern coast up to about 1 km inland. These deposits average 20 meter in thickness and carry 10 to 14% heavy minerals, of which ilmenite, zircon, leucoxene, and rutile constitute about a half. Modern placers. Modern placers, unlike most paleoplacers, are quite diverse in their valuable mineral content. Alluvial placers on hill slopes develop unaided by any stream action and require rich lodes as parent materials like cassiterite, gold, barite, gemstone, and wolframite placer deposits. Alluvial placers are most diverse, having contributed huge quantities of gold, cassiterite, platinum group of elements, diamond, gemstones, river pebble, phosphates, and high purity, well sorted quartz sands. Beach placers are best known for their multi-component ores and also for gold and cassiterite. Alluvial placer gold deposits occur in California, the western states of Nevada, Idaho, and Utah, and in Alaska Yukon Territory in USA, in Australia, New Zealand, Central Africa, Peru, Bolivia, Chile, New Guinea, and Siberia. Alluvial gold placers are being mined at present on a large scale in Alaska, California, Colombia, Siberia, Central Africa, and New Guinea. Beach placer gold, comparatively much finer due to longer transport, is best exemplified by the Nome deposit in Alaska, a littoral zone deposit subsequently raised. Placer gold particles display bewildering variety of texture and size, ranging from floors, colors, dusts, flakes, and discs to rounded grains, pea-sized nuggets, and irregular nuggets up to a few tens of kilometers. Microscopic, microprobe, and spectroscopic examination of placer gold particles reveal numerous features that relate to the primary source, the distance, and environment of transport. Trace element signatures can discriminate among mesothermal quartz sulfide vein ores, greenstone belt gold deposits, and shallow epithermal gold sources. For instance, the placer gold deposits of prepolar Urals in Russia, occurring along alluvial valleys and terraces of quaternary age, are geochemically distinct in different regions with dominance of silver, silver mercury, silver copper, and silver copper mercury in solid solution. The silver mercury rich variety had its source in near surface epithermal deposits. Ultrafine inclusions of sphalerite, galena, and or chalcopyrite indicate the derivation of placer gold from either gold-bearing massive sulfide deposits or porphyry type source. Occurrence and intensity of folding of flaky gold particles and scratch markings on grain surface constitute a measure of the distance traveled and can be calibrated as such from known situations. The increase in fineness due to selective dissolution of silver and or orthogenic overgrowth of gold can be used as a measure of distance of transport. Placer deposits of cassiterite rank second in value next to gold placers and currently supplies nearly 2/3 of the global supply of tin ores. Alluvial, and beach placers of cassiterite originate from weathered lodes and stockworks in granitoids. Large alluvial and significant alluvial cassiterite deposits in sinkholes in bedrock marbles occur in Kinta Valley, Malaysia, while Indonesian occurrences have a large component of alluvial ores recognizably from high concentration of unweathered cassiterite and associated angular grains of other detrital minerals. Stream placers formed from materials derived from primary sources and alluvial cassiterite preconcentrations occur along river channels. Minor amounts of stream placers are exploited in Thailand, Tasmania, China, Zaire, Nigeria, and Bolivia. In India, minor occurrences of stream placer cassiterite derived from pegmatites are found in the Bastar district in Madhya Pradesh. Platinum placers, both stream and beach types, had been the single source of supply of platinum group elements for over 100 years since the first discovery in Colombia in 1786. About one-third of the world production of platinum metals come from placers. Placer platinum finds similarities with placer gold in several respects. Like placer gold, it occurs as dust, flattened pellets, and rarely as nuggets. The platinum content of the ultramafic source for placer platinum restricts the occurrences to terrains with peridotitic and ophiolitic hinterland provenance. In the Ural mountain region, Paleozoic peridotites constitute the source material for stream placer deposits of platinum. Major supplies of placer platinum comes from Tasmania, Colombia, New South Wales, Papua, Ethiopia, Panama, Japan, and Alaska. Diamond placers from Brazil and India constituted the only two sources until 1871, when the first kimberlite pipe was discovered at Kimberley, South Africa. At present, the major global supply of industrial and gem variety of diamond comes from placer deposits in Zaire, Ghana, Angola, Guinea, Sierra Leone, Liberia, Brazil, Africa, Siberia, Australia, and a few other countries. The diamondiferous marine gravels in Namaqua Land, South Africa, occupy terraces up to 65 meters above the present sea level and occur discontinuously over 320 kilometers. Placer gemstones, which include gem varieties of corundum, beryl, chrysoberyl, zircon, and garnet, mostly occur as alluvial or stream gravel placers. These are mostly derived from weathering of complex zoned pegmatites, contact metamorphic and or regional metamorphic rocks. Some of the best rubies come from alluvial placers and stream gravels in Magok, Myanmar. Alluvial placers with rubies are also known from Cambodia, Thailand, Sri Lanka, and Kenya. Sapphire in alluvial gravel deposits is known from Thailand, Cambodia, Sri Lanka, and India. Sri Lanka is the principal source of placers with cat's eye and alexandrite. Tanzanite, the blue gem variety of zoisite, is restricted to a few localities in Tanzania. Multi-component shoreline placer deposits occupy a unique position among the different varieties of ore deposits in terms of their lateral extent, like in eastern Australia, where they occur along a 1,200 kilometer stretch from north of Brisbane to south of Sydney, or in the coastal Kerala and Orissa in India. B. Distinct geotectonic setting along Atlantic type passive continental margin, like in Brazil, Florida, east and west coast of India, and C. Vast, deeply exhumed granite, charnockite, granulate distributive provinces in appropriate climatic zones. D. Well-developed, steady and fixed conduit systems. And E. Multi-component character that ensures simultaneous recovery of several co-products. The Australian and Indian occurrences, along with those in South Africa and the southern US occurrences in Florida and Brazil, share these commonalities. In Australia, modern beach sands as well as landward extended Pleistocene beach sands and Holocene and Pleistocene dunes carry rich placer deposits. The beach sands of Travancore and Quilon in India contain 50 to 70% ilmenite and 2 to 5% monazite, along with zircon, rutile, and garnet. Brazilian beach sands contain about 51% zircon. The beach sands in Australia contain up to 75% zircon. Black sands containing magnetite, ilmenite, chromite, and other heavy minerals are found in Oregon and California in USA, Japan, Egypt, and New Zealand coasts. Paleoplacers, the WITWATERSRAND example. Precambrian gold and or uranium-bearing conglomerates that have come to be known as the WITWATERSRAND type have been found from some 30 other localities, of which the Elliott Lake and the Blind River district in Canada, the Serra de Jacobina field in Bahia, Brazil, and the Turquoise gold field in Ghana are the most important. Several commonalities seem to interrelate them genetically, such as A. Dominantly oligomictic, well-rounded nature of the quartz pebbles, B. A matrix of well-rounded quartz grains and mica, cerussite, chlorite with particulate gold and or uraninite, C. Prolific accumulation of detrital pyrite, D. The presence of a large suite of accessory heavy minerals from which magnetite is conspicuously absent, and E. Moderate grade of regional metamorphism. The WITWATERSRAND gold field, discovered in 1886, constitutes by far the most spectacular super large metallogenic province, having produced about 42,000 tons of gold, 2,940 tons of silver, 26 tons of platinum group elements, and about 840 tons of mercury up to 1990. Additional interest since 1944 has been the discovery of uranium ore with a very conservative estimate of 5,32,735 tons of uranium reserve. The field boasts of having more than 60% of estimated global resource of gold, being the third largest source of uranium ore and containing the world's richest single ore body at Welcome and the world's deepest mine, about 3,965 meters at the western deep levels, Carlstonville. The supracrustal sequence, about 18 km thick, of WITWATERSRAND intercratonic structural basin of the Kapwal Craton comprises the Dominion group, the WITWATERSRAND supergroup, and the Ventersdorp supergroup in that order of younging. This preserved relic of the once more extensive basin complex lies along an arcuate southeasterly concave belt whose outer margin, 480 km by 100 km, houses the 6 known gold fields, as shown in figure 7. A northwesterly trending regional upwarp coincides with axis of arcuation of the belt. The supracrustal rocks evolved during a time span of 360 million years. The adjacent source province reveals an age range of 3,200 to 2,900 million years. Several generations of granite, some as young as 2,727 plus or minus 6 million years, have been recorded from areas adjoining the basin. Many of these granites, often hydrothermally altered, were intruded sporadically before and during the 360 million years of basin evolution. Paleogeographic reconstruction of the environment of formation of the 6 major gold fields allows identification of entry points of sediments, as shown in figure 7, to freshwater lake or shallow water inland sea from the distributive provenances through river systems confined between structural domes of basement rocks and displays the influence of domal structures on the location of prograding fluvial deltaic fans with fan head, mid fan and fan base of progressively finer materials outwards, as shown in figure 8. The mid-fan facies with medium-sized pebbles have the highest concentration of heavy minerals, and the coarsest fan head facies have lower gold tenor. Maximum uranium occurs at the distal fan base facies. Paste streaks in all the facies are confined to braided paleochannels, as shown in figure 9. The ore-bearing conglomerates occur as horizons within the central rand group of the WITWATERSRAND supergroup. Among the gold fields, Welcome Goldfield has 4 auriferous uraniferous horizons, Klerksdorp 7, the Carltonville 3, the Westrand 10, the Eastrand 9, and the Evander 1. These ore-bearing conglomerates vary in thinness but generally less than 1 meter thick. These horizons occur A. on anastomizing scoured surfaces representing braided stream channels, and B. less commonly on flat, extensive intraformational stratigraphic breaks or along regional unconformities. Carbon seams leaders up to 10 centimeter thick host some of the richest gold concentrations. These carbon seams occur in all the gold fields. These seams constitute algal mats built by Proterozoic microorganisms. The ore-bearing conglomerates contain oligomictic pebbles of vein quartz and chert, which constitute about 80% of the bulk material of the ore-bearing conglomerates. Matrix of the conglomerates primarily comprises quartz, cerussite, chlorite, and numerous heavy minerals. About 70 ore minerals in the matrix have been identified, of which 40 are clearly detrital in origin. Pyrite of 3 generations, namely detrital, diagenetic, and metamorphic, constitutes some 15% of the matrix. Other minerals include sulfides, oxides, native metals, and uranium-bearing thucolite. Magnetite and unaltered ilmenite are also notable absentees in the list. Origin of the deposits. Even after more than 100 years of extensive mining and research, the origin of these deposits remain controversial, although the most favored model is the modified Placer theory. The controversies center around 3 conceptual aspects: the mechanisms of emplacement, the time of ore concentration, and the source rocks from which such huge tonnage of gold and uranium could have been derived. Modified Placer theory of origin considers the following possible sources for the gold uranium mineralization. Number 1, older granite greenstone source. Number 2, source in sedimentation granitoid related hydrothermal mineralization in the distributive province. Number 3, physical reworking of proximally deposited gold rich pyritic sulfide facies exhalites. These exhalites are believed to have formed near hydrothermal discharge vents generated by extensive shallow marine volcanism. Number 4, dissolution of trace amounts of gold from source rock, transport to and precipitation within basins, and subsequent intrabasinal particle reworking, according to Reimer 1984. The modified Placer theory origin argues for detrital sedimentary origin with subsequent remobilization of gold, obliteration of some pristine attributes, and overprinting of hydrothermal-like features during diagenesis and metamorphism. Gold, uraninite, the first generation pebble pyrite, and the thucolite balls are all assigned detrital mode of transport and the accumulation along with other accessory minerals in the matrix. Chlorite, cerussite, rutile, younger pyrites, etc. possibly represent diagenetic or metamorphic reconstitution products. Regional metamorphism is invoked to explain the absence of magnetite and ilmenite, which presumably reacted with the sulfur derived from the first generation pyrite to produce the metamorphic pyrite or pyrrhotite and rutile. The roundness and sorting of uraninite, pyrite and thucolite pebbles are consistent with a detrital origin. Their survival during fluvial transport is ascribed to the externally low pressure of oxygen in contemporary atmosphere. Summary. Placer deposits may be defined as a special type of clastic or detrital sediment, unconsolidated or semi-unconsolidated sedimentary rock or its metamorphic equivalent with economic grade concentration of one or more valuable, dense, resistant minerals. Placer minerals having these properties in varying degrees include cassiterite, chromite, columbite, tantalite, diamond, garnet, gold, ilmenite, magnetite, monazite, platinum, ruby, rutile, sapphire, zircon, and rare earth elements. According to an estimate made in 1989, about 48% of gold, 55% cassiterite, and 18% of uranium ore of the world occur in detrital sedimentary placer deposits. Traditionally and genetically, placer deposits are classified as number 1, residual placers, number 2, alluvial placers, number 3, stream or alluvial placers, number 4, beach placers, number 5, offshore placers, number 6, Aeolian placers. Mineral concentration in placer deposits possess 3 common attributes. They all have high specific gravity, high malleability, toughness or hardness, and are all chemical weathering resistant. Their source of placer deposits could be A. Lean or rich lodes including pegmatites, disseminated ores and stockworks. B. The underlying podzolized bedrock itself in case of residual placers. C. The accessory minerals present in the rocks of the distributive provenance. For some multi-component beach placers, the source regimes are usually the vast, deeply exhumed metamorphic igneous complexes. Residual placers accumulate immediately above a bedrock source by decay or removal of the lighter rock materials, and they may grade downwards into weathered veins. In residual placers, chemically resistant light materials may also occur. Residual placers formed over carbonatites are important as producers of apatite. They are also sources of zircon, bedillite, magnetite, and other minerals. Chemically resistant anatase deposits developed in the weathered overburden of 3 alkalic stocks in Parana Basin, Brazil, constitute some of the world's largest titania deposit. Alluvial placers are formed upon hill slopes from minerals released from a nearby source rock. The heavy minerals collect above and just below slope of the source, and the lighter non-resistant minerals are dissolved or swept downhill by rainwash or are blown away by the wind. Cassiterite is obtained in abundance from alluvial deposits in Myanmar, Thailand, Vietnam, Zaire, Nigeria, Australia, apart from Malaysia. Stream or alluvial placers were once the most important type of placer deposits and have yielded large quantities of placer gold, cassiterite, platinum, and precious stones. In a stream bed, relatively coarse heavy minerals can be expected to be concentrated in riffles, plunge pools, eddy pools in rapids, and potholes. The confluence of a swift tributary with a slow master stream and rapidly flowing meandering streams provides sites for heavy mineral accumulation. Gradients measured out at a little under 1 to 175, that is moderate gradient of about 6 meter per kilometer. Beach placers contain economic concentrations of cassiterite, diamond, ilmenite, magnetite, monazite, rutile, and zircon. Examples include gold placer of Nome, Alaska, diamondiferous gravels of Namibia, Angola, ilmenite, monazite, rutile sands of Travancore and Quilon, India, ilmenite, zircon, leucoxene bearing sands of Richards Bay, South Africa, rutile, zircon, ilmenite sands of Eastern and Western Australia, and titanomagnetite sand of North Island, New Zealand. Recent and sub-recent beach placers occur at different topographical levels owing to Pleistocene sea level changes. Offshore placers occur on the continental shelf, usually within a few kilometers of the coast. They have formed principally by the submergence of alluvial and or beach placers. Example, tin placers of Indonesia and Hainan, China, monazite-rich sands off the north and southeastern coast of Sri Lanka. Aeolian placers are known to have formed by the reworking of beach placers by winds. High-grade Aeolian deposits occur at Richards Bay, South Africa on the Natal coast and occur in a belt along the modern coast up to about 1 kilometer inland and rest on a platform at 20 to 40 meter elevation. The deposits average 20 meter in thickness and carry 10 to 14% heavy minerals like ilmenite, zircon, leucoxene, rutile and monazite. Precambrian paleoplacer deposits encountered in Witwatersrand Basin in South Africa and some 30 other localities contain large accumulations of gold and or uranium bearing conglomerates. These deposits have several commonalities such as A. Dominantly oligomictic, well-rounded nature of the quartz pebbles. B. A matrix of well-rounded quartz grains, mica, cerussite, chlorite with particulate gold and or uraninite. C. Prolific accumulation of detrital pyrite. D. Presence of a large suite of accessory heavy minerals from which magnetite is conspicuously absent. And E. Moderate grade of regional metamorphism. The Witwatersrand gold field constitutes by far the most spectacular super large metallogenic province, having produced about 42,000 tons of gold, 3,000 tons of silver, 26 tons of platinum group elements and about 840 tons of mercury up to 1990. Additional interest since 1994 has been the discovery of uranium ore. This field is the third largest source of uranium ore. The gold and uranium deposits of Witwatersrand Basin are considered as modified placer theory of origin by majority of investigators.